Welcome to our MATLAB workshop. This is our first workshop of winter term. It's going to be a very introductory one. We have the slides here in this link. Please make sure to get this link just in case you want to go back and redo any exercises you want, because they're very informative. Today, Chris and Bernard will help us with presenting. We will go over the basics from importing data, adding, multiplying matrices together, how to deal with matrices, what is a matrix, and then plotting, importing data from an Excel sheet. And then we're going to combine all of these bits and pieces of information into one project that Chris is going to explain us very shortly, and then we will go on from there. And if you want to stick until the end, I will explain a little bit of signal processing, how you can use MATLAB and how helpful it is with these other tools. So take it on from here.
Awesome. So hello, everyone. My name is Bernard, and I'm going to be covering the intro to MATLAB part of this section. And so let's get started. So what is MATLAB and why should we use MATLAB? Well, MATLAB is a program for doing numerical computation. It was originally designed for solving linear algebra type problems using matrices. So MATLAB is all about the matrices. Its name is derived from Matrix Laboratory, or MATLAB, as you can see there. And it seemed like most of you had MATLAB installed or are using the online compiler. So if you haven't, well, you can use if you go on matlab.mathworks.com, you can sign in with your Drexel email. You just need to confirm your Drexel email. So yeah, it would take like 5 minutes. So if you're paying attention in like the video, you can pause the video right now and then sign in through there. So MATLAB is like divided by like 4 parts. So there's I can just show you. There's the folder, there's the workspace, there's the scripting, and then there's the command window down there. And so you have the command window, live script, function files, scripts. So we're going to go all over that later on. And so the MATLAB environment is command oriented, meaning like everything is a command basically. So if I type x equals 1 in the command window, it will return x equals 1. But to suppress that return, if I don't want it to be displayed, I have to use a semicolon. So if I do that, it won't do anything. But now if I type x, it will show the value of x, which is 1. All right. So like I said before, MATLAB is all about the matrices. So a matrix is a rectangular arrangement of numbers into rows and columns. So here we have matrix A, which is a 2x3 matrix. And I'm going to show you how to declare matrices using MATLAB. So we have a matrix, a simple matrix here, -2, 5, 6, and 5, 2, 7. So we could write that, -2, 5, space, 6. So all the elements are separated with spaces, and then the rows are separated with semicolons. So 5, 2, 7, and then run this, and it should say that C is -2, 5, 6, 5, 2, 7. And then to access the individual elements in the matrix, we have to use indexing. So to do that, we need to use parentheses right here. So we would have the matrix name, and then the rows, and then the columns. And MATLAB is like, unlike other programming languages, the indexing starts at 1 instead of 0. So if I want to access -2, for example, in C, I would have to type C11, and then that would bring up -2. You can also make multi-dimensional matrices. So you can make 3x3 matrices here, as you can see. And there's like special functions that you can use to make the matrices for you, just so you don't have to type everything in. For example, this function right here is a function that makes a matrix of zeros. So I see that you guys are filling out the MATLAB. All right. So it seems like everyone kind of wants an introductory. So I'm just going to go a bit slower, and feel free if I'm going too fast to say something in the chat, and I can explain something more to you. All right. So MATLAB also has variables, and they are case sensitive. They can contain about 63 characters, and it must start with a letter followed by letters, digits, and underscores. And we have special variables called like ands. You can see ands right here. It just returns the previous answer. Pi is just pi. Exp is the function for the Euler's equation. So like if you recognize that number right there, you probably do, it's E. And then inf is just infinity. And you can also have negative infinity. And you can experiment with these later on. And so we also have operations. So like I said before, MATLAB is all about the matrices. So when you see a naked operator like this without a dot, that means it's like a matrix operation. And with the dot, it's an element by element operation. I'll explain that more in a bit, but let's just look at these for a second. So we have the power, and then we have the multiplication, division, addition, subtraction, and then assignment. And you can see all the symbols here. And if you have the slides pulled up, you can refer back to this slide just so you remember them. So by default, the multiplication symbol actually does a linear algebra type matrix multiply. And you can see that formula in a 2x2 matrix here, but it gets more complicated when it's like a 3x3 matrix or like a 2x3 matrix. But a simple formula is a 2x2 matrix, and you can see that here. Yeah, cross product or dot product or however you want to call it. And so here's an example right here. We have 1, 3, 2, 4. So I declared that here, and then B, obviously, I declared that here. And then when we multiply, a matrix multiply them, it uses the cross product or dot product, and you get the dot product here. But if you use a dot before the multiplication sign, like here, you actually multiply each element to each other. So it would be 3 times 1 is 3, 4 times 5 is 20, 1 times 2 is 2, 0 times 3 is 3. So you could kind of see that there. You're kind of multiplying all the elements to each other wherever their index is. So we also have commonly used functions, and the most important one here that you should remember and memorize would be doc term. So for example, if I'm confused about what numel means, like I forgot what numel is, I can just type doc numel in the command window, and then it will bring up the wiki for MATLAB and tell me all about that function. And I can even do it with an operator. So like a colon, for example, is an operator in MATLAB that makes ranges. And yeah, you can read all about it and stuff like that. So numel returns the number of elements. So numel A would return 4 because there's 4 elements in A. And then zeros, like I said from before, it makes a matrix of zeros. So I can make a 4x4 matrix of zeros. I can make a 2x2 matrix of zeros, and I can make just 1, 0, or 5x5. And yeah, square root, that's kind of self-explanatory. Average, explanatory. Random, I don't really know what that one does. Oh, there you go. It does the same thing, but random values, random floats. Okay, so let's move on. So we have symbols. The greater than symbols mean command prompt, and that's down here. You can see that down there. And if you want to continue a statement to the next line, you can add dots to it and then press enter. And then you can separate long lines of code into two, just so it's easier to read. And then to separate statements and data, that's more important when you use a comma. That's more important when we do like function calls and like weird return lists and stuff like that. And we'll show you that later. And commenting, you use the % symbol. So hello world comment, you can do that. So to suppress the output, again, it's a semicolon. So if I put a semicolon here, it won't say it anymore. So as you can see there, I ran the matrix program, but it didn't say anything. But it still edited the functions. I mean, the variables. To specify range, you use the colon. So for example, 1, 2, it goes 1 to 2, 1 to 5, it goes 1 to 5. And then you can actually edit the increment in between those. So like I can have a 1/2 in there, and then it would add by a half each time. And so if you get confused, you can always just do that and then read the wiki. So as you can see here, there's different types. So there's just two operations, I mean numbers. So that's like here. So that's a beginning and then the end. And then the I in here is actually the incrementer. So if I do start at 5 and then increment by 5 to 30, it will do that. So this is the increment in here. This is the end. This is the start. This is the start. This is the end. Okay. Brackets, enclosures, array elements. So that's how we made these matrices from before. We use brackets. And then to separate the columns, we use the semicolon in there. Parentheses encloses function arguments and array indices. Like I said from before, to access the array index, you can do this. Oh, it's because I didn't run it. There we go. To access that, 1, you would do 1, 1. Okay, so now we have conditional statements. And before I get started on this, I want to show you what clear and CLC does. Oh, we have a question in the chat.
So can you guys hear me? Yeah.
Yeah.
So A and B is matrix multiplication. So go back to the slide.
Yeah.
So if we notice, there's this pattern when you do matrix multiplication, that is row column, right? So it is each element is gonna, yep, right there, exactly. So it's gonna be the first element of the other one is going to be A, E plus BG, and then we do this for every other element. Dot products, it's a bit difficult. I mean, you could say it is dot product for that one, but the correct term is matrix multiplication. You guys will learn it. If you haven't taken linear algebra yet, you will learn it soon, so don't worry too much about it. Just remember that this is the linear multiplication, but most of the times we don't use this, and we want to use just to multiplicate each element by each. What Bernard showed with, for example, dot multiplication. That's also very important. So let me know if if that kind of explains it, and I will hop in the chat to explain more if needed.
Yeah, it's a different algorithm than the dot product when it's like bigger than 2 by 2, I guess. Is that right? Yeah, okay. I see nodding heads, so I'm gonna assume that's right. All right. So clear basically just clears your workspace, which is right here. So your workspace stores all your variables and like answers and things like that, figures, whatever. So if you type clear, it will get rid of all that. And then CLC, that command just clears your command window. So like if you ever get confused again, you can just do doc clear and then it will show you what it does. All right. So here we have an if statement with a list right here. So we have vec, which has 11, 22, and 33. And then this if statement right here is going to check if every element in that matrix is less than 12. So if it is, it will type if ed. And then if it isn't, it would type else ed. So if we run this code, you can see that it is else ed right here. So this file is an example of a live script, and you can make one using this live script. And it's a little different than the regular file which is .m, whereas this doesn't display the outputs on the side here. Well, this does. And there's a lot more into like what makes a script live, and like you can add more like headings and like text with it to explain your code. And it's a little more it's a bit slower, but it is very useful for debugging programs because like it lists where it is ran. So here it since all the elements here aren't less than 12, it will type else ed. And then rec is just an array of 11s. So rec is actually less than 12, so it will say less than 12. And if you ever programmed before, you probably said, "Oh wow, that's cool," because like this would be more involved than like for Python, for example, because you would have to iterate through the list. And this really shows the power of MATLAB because it's matrix oriented. Like it has these operators that works on matrices like that. So then we have loops. So with a for loop and then a while loop. And the for loop repeats for specified number of times. So you specify it with the colon operator, and it always executes the loop at least once. Can use plus or minus increments, and you can use break to leave a root loop. And then while will do computational loop only if the while condition is met. So the while condition here is test is greater than 1, and it can loop forever if variable is not updated. So you got to be really careful with these while loops and make sure that your variable is incremented. So I'll show you an example of that here. So we have this function called ones. So that basically just creates a matrix of ones. So it's a 1 by 10 matrix there. And then F out is just an empty matrix of zeros, 1 by 5. And then we have these loops. So for n equals 2 colon 6. So 2 is the starting position. So starting index. And then 6 would be the ending index. So for n 2 to 6, it's going to do this operation. It's going to edit our matrix over here that we initiated. So if I run this, it's suppressed, so it doesn't output. But now if I type X, you can see that it edited the matrix that we started here. So it edited it from 2 to 6. So 1, 2, 3, 4, 5, 6. And as you can see, 7, 8, 9, 10, they didn't get edited because it's only from 2 to 6. Okay, so then we have F out zeros. It's filled with zeros. And then we're going to start at 1, increment by 1, and then end at 5. So F out is going to be squared. D squared. So 1 squared is 1, 2 squared is 4, 9, 16, 25, and so on. So 5 squared is 25. All right. And then this is how you index through a matrix, if you can remember. So this will be like, this will count to 1, 2, 3, 4, 5, and this will change it to 1, and this gets changed to 1. And then you can probably see how that replaces it with this value using the assignment operator. And then lastly, we have this test where it's test equals 0. It's just a 0. It starts at 0. And then while test is less than 3, we're going to do this operator. So since test is still 0, it will be less than 3. And it will do test equals test plus 1. So test will become 1. And if we run this, you can see that this while loop will count 1, 2, 3. There you go. That's how you do simple while loops. Okay. Anyone confused with that? Okay, good. All right, so now we're going to get into the nitty-gritty. We have a function definition. And so to declare a function, you can actually just make a new script and call it function right here. And I already have one over here, and I'll explain that in a bit. But the basic skeleton of a function is here. So we have the output arguments in this list before the function name. So we have however many output arguments that we want. So you can just put any arguments in there and separate them with commas, but make sure you put the square brackets in there. And then we have the function name here, function name, and then the input arguments or parameters. So you can separate these with commas as well. And I'll show you an example now where we're going to make a function example with function add, called function add. So we're going to store the result in sResult. The function add is the name. And then A and B are the parameters. And you notice here that it's separated by a comma. And then what it's going to do is it's going to add A and B. A and B. All right. And since it's in our current folder, I should be able to just call this function. So if I do function add 65, 43, oh, I misspelled it. It will return 108. And I can store that in a variable if I wanted to. 54, 21. There you go. And theoretically, we could do lists as well. There you go. So 1 plus 3 is 4, and then 2 plus 4 is 6. So this is kind of like the polymorphism of MATLAB, where you can use matrices and variables, because in the end, everything is a matrix in MATLAB, even the variables like ANDs. ANDs is just a 1-by-1 matrix. That's what MATLAB treats it like. Okay, so hopefully that wasn't too bad. And now we're going to get into making plots and pretty pictures, as we like to call it. So we do that using this plot over here. And as you can see, it makes these pretty little graphs and really easy to read. And you can edit like the legends, the titles, the X labels, Y labels, and so on. So here's an example, a basic example. And so we have CLC, which clears the command window, clear all, which clears all our workspace and figures. And then we have 9.8, which is, you probably remember as the gravity, special number for gravity acceleration. And then we increment by 1 over 27 from 0 to 3. That's our time. And then our angle is 15, 15. Start at 15, increment at 15, by 15, and end at 75. And then we have this cosine D. Cosine D is kind of like cosine, but it uses degrees instead of radians. And so if you have the slides open, you can actually just copy paste this from the slides into MATLAB if you make a new file, and then it should work out into making this plot. So we calculate it here. It's kind of like an object falling from the sky, and we use cosine and sine to do that. And remember, they're in degrees, and then we plot using plot, and then the X value, and then the Y value. And then there's different parameters where I'm going to show later on. But for now, let's start with X1 and Y1 here. And so when it plots, it does this. Okay. And I encourage you to try this one because this is like what MATLAB is about. Most of the time I'm using MATLAB to plot things. So if I run this section, it's going to make the figure. So I'm gonna wait like 2 minutes. If you have a successful plot, please type in chat that you do, so I know that when everyone's done. Oh, you actually don't need to download MATLAB. You can sign in using a Drexel email with this link right here. So if you open up a web browser and sign in with your Drexel email, MATLAB on the Firefox is perfectly fine, or Chrome, or whatever browser you use. So while it downloads, you can probably just do that. No problem. If you guys want to see the slides that we created, I linked them again in chat. Is anyone having trouble with this? You feel free to unmute.
Posted. I wanted to ask if the code for this is somewhere.
Oh
If you
yeah.
posted it somewhere.
Yeah, I posted it in the slides. So if you click that link,
Yeah.
line 10. Okay, so let me look at the slides. So you copied and pasted here. Line 10 is plot. Oh man. The heck?
Which slides is a link for the code on?
This one. I sent it again. IEEE MATLAB slides.
I have that one open, but
it's on slide 18.
oh, 18. Oh,
Yeah, sorry.
Thank you. Sorry, I just joined so late, so I'm kind of behind a little bit. Oh, thank
No
you.
worries. So the C in the plot function here is actually it stands for cyan. So you can change the color of the graph or the line using these letters, and I'll go over that in the next slide. So if I do blue, it changes it to blue, and then if I do like magenta, it will do magenta. There you go. Yep. All right. All right. So if you need to create a new file, you can go over here in the editor tab and hit new script, and you can save that whatever you want to name it. Oops. I'm just going to delete that. All right. So is everyone all right? I don't remember when I started this. So I don't know how long it took. Okay, I'll give you guys like a couple more minutes.
Hello.
Hi, can you share the code, please, for a second?
Absolutely. I didn't type anything else into it. I just copied and pasted.
Okay. So what issue does it give? I see. Try at after 0.5. Oh, I think you have an issue there at line Y1.
The first line?
At line 9.
Oh, gotcha.
Do you need the part 0.5 there?
I don't know. I just
Oh,
copied
you're
the
missing parenthesis.
Okay.
So actually, right, go to the thingy again. So that one, press enter and try and run it now. Yeah, just give it another name, like, yeah, whatever. Yeah, it's okay. Does anything pop up?
No.
Okay, let's join the thingy again, and I will check this.
No worries.
I don't know why it's doing that.
Did you figure out what was line 10 there?
I think this is line 10, because if you copy paste it, like it gets
But
screwed up.
does it need line 10?
I don't think so.
Yeah. Try and remove line 10.
Yeah, I don't know why it's linear in this one. Yeah, I'm gonna copy this and then paste it here.
You're forgetting the minus. It is minus the thingy.
Oh, it's minus. Okay. So it's over here.
Yep, it is a minus.
Sorry,
Yeah, that should fix it.
I had the wrong code in the slides. My bad. All right, so if I run this, yeah, there you go. It's the minus here, because that makes sense, because this is the position equation from physics. All right. There you go. So if you change it to a minus there, it should work. Let me know if you guys are ready to move on. Am I still sharing my screen?
Yes.
All right, good. Okay. Did the minus sign fix it for everyone? Okay, great. Okay, so I'm going to move on. All right, so the next slide goes over the basic colors. So like I said before, we have red, and the short name is R. Green, G. Blue, B. Cyan, C. Magenta, M. Yellow, Y. Black, K. White is W. So I can try K. Oops, it's getting weird. Run. And it turns the line to black. Exit that for now. And you can also like move around in this graph that you made and like do some funky stuff, like select the data point. but yeah. Zoom in, zoom out, and then press the home to reset it. Okay. So that's the basic colors. And now we are going to get to something more involved, which is subplots. So I'm going to take my time here. So this line, fig equals figure, name, wow, look at these subplot. This just initiates a figure window. Okay, so we name it. So we're saying, oh, we're going to give you the name. And then the next parameter after the comma would be, wow, look at these subplots. Okay, so it makes a window. So if I do that here, fig equals figure, name, hello world, it should work. Yeah, there you go. It's an empty figure window. Exit that out. All right, so there you go. And then we specify how many subplots we want. So here we have two subplots, one right on top of each other, 1, 2. So we want 2 rows. So this is a row, this is a row, and this is the column. So we have 2 rows, 1 column. And then we do subplot the amount of rows and then the amount of columns 1. And that 1 is indexing the subplot we have. So this is 1, this is 2. So 1, 2. Okay. So we saw this from before, plot t this time, and then x1. So this is the x values, these are the y values. And then we're saying I'm going to give you a color next in the next parameter with this quotations color, and then we're going to give it the color, which is b. And you don't need this, but you need the specific order if you don't put it in. But this is like a convenience factor to just make sure that, to tell MATLAB that you are about to give them a color type. And then this title function here, it will add a title to the subplot. So it has to be after the plot and subplot. So plot 1, we're going to label it as plot 1 here, and you can see it there. And then xlim, you specify the axis limits of the graph. So this goes from 0 to 1. So 0 to 1. And then we have the same thing, but with y's. So y limit goes from 0 to 5. 0 to 5. And then x label, so you can label your plots, your beautiful plots that you make. That is t and then x1. And then grid on just turns on the grid that you can see here. So the grid is now on. And if you don't have that, you kind of have a blank white page in the background. And then the bottom here just says the same thing, but the indexing, plot index is 2. So 1, 2. And then we have the grid on different x limits, and it plots the other function y1. And then we lastly, the last function here is subtitle, SUP title. And that brings a super title, as I like to call it, up here. So you can say that to whatever you want. And I'm going to copy paste the code in chat for everyone to. So this goes under the previous code that we made up here. right here. So if you can just copy and paste that and run your code from the MATLAB, the Zoom chat, we can move forward. So if you successfully copy paste it from the Zoom chat, let me know in the chat, please. And if you're watching the video, you can pause the slides now. Hey, cool. So if I run this, it does that. Okay, awesome. So we actually, if you look at this figure, we can like save it and then save it as a figure. We can save it however we want. We can do PNG if you want, if you have a homework assignment and it needs detailed graphs. All right, so I just got a question in chat. If you want to subplot 4 of them instead of 2. So there's actually like different ways of doing that. You can have a 2x2 matrix of subplots or like a 1x4. And we can do doc subplot, right? And it will show us how to do that. So here's an example of what I gave. So 1x2. And then here's an example of the 4x4, right? So if you do doc subplot, you should be able to see this example when you scroll down. So it's kind of like the same thing, but instead of the index being there, instead of being like 2, 1, it's going to be 2, 2. And then you index 1 and then index 2, index 3, and then 4. Right. So, and then it turns out like that, but you can do that in the project window that time we have. And you can actually do like weird stuff like this, where the subplot takes up 2 subplot spaces, and then you can do a lot with these. A lot. But yeah, the documentation is all there. So let's move on to figures. So I'm going to hand the mic over to Chris, and he will tell you more about the project and give you the fundamentals that you need to start it. So I'm going to stop sharing my screen.
All right, thanks, Bernard. That was a really great intro for everyone. And everything that I'm going to be working you guys through, it's going to be using all the same tools that he just walked you guys through and taught. So I will share my screen. Okay. Oop. Hold on 1 second. Okay. Just trying to move my, all right, you can see it? Okay, cool. Screen sharing, and we're going. Wow, I feel like a boomer. Can't open this. Where is the speaker view? Okay, all right. So first thing we're gonna talk about is really quick is opening Excel files and then using that to plot. So we just kind of, walked through how plotting in MATLAB, you can, add all these colors to your graphs. I'm also going to show a couple examples where we actually can plot points and then change the shape of those points, as well as, the edges, the colors of the edges, and the colors of the faces. And so, you might ask, why would you bother doing that if, whoa, I have an Excel sheet with all the data in it, I'll just use Excel to plot. Well, we have a lot more control in MATLAB because we can set our line widths and we can set the color and we can name our figures, and it's a lot easier to, as Bernard showed, actually save it as a PNG or a PDF and then put it into your homework assignment or something like that. Some of the functions that MATLAB has for reading and looking at Excel files is we have XLS info, which gives us the status and the number of sheets. And status is usually just basically just says if it's a Microsoft Excel sheet or if you're on some other operating system or using something other than Excel, which I feel like most people would be using Excel, but if you're not using Microsoft Excel, it'll probably say, let's see, am I recording? Hold on one second.
I think Ray has started.
We're still recording. We've been recording.
Oh,
all right.
Sorry.
Yeah, it's okay, Bernard. I'll go back to the slides then. Yeah, so Excel info kind of gives us an indication if the file can be read, if it's an Excel sheet, and it gives us the names of the sheet in the Excel file. And then XLS read can read the entire spreadsheet or a range of cells in the Excel file, and then actually then saves we can save the data and the name of the sheets in MATLAB. So I'm going to super quick pause share so I can throw in, oh, Bernard already threw it in. Thank you, Bernard. So if everyone can just download that Excel sheet, you'll see that we're going to have just a straight column of just some random numbers. And so all we have to do, I'll share my screen again. All we have to do is we can make a matrix here, or make a list, name status sheets, and equal it to the function XLSF info, and then our file name, which in our case is the IEEE _MATLAB _data. And then same thing with XLS read. And if we run this, we'll see in our workspace, it gives us status, which just says Microsoft Excel spreadsheet, just kind of telling us what we already know. That is, it's a Microsoft Excel spreadsheet. Tells us how many sheets there are, or the name of the sheet. First name of the sheet is sheet 1. And then it gives us data. So we have A is our data, so we could call that whatever. But that's the first thing that XLS read will return. It'll actually return the data from the cells and then read that for us. Oh, I'll just close that figure. So if we want to plot this, which we talked about figures, and you can call a figure and you can say like, okay, I want to have a figure. But if you're just doing something really quick, or you have Excel, data from a lab, you can just directly start calling plot, and it'll actually create a figure, an unnamed figure, and it'll just be called figure 1. But you can actually plot all of this. So I think we have 30. Yeah, we have our Excel data is 30. So if everyone's run XLS read with the string here, oh, and then this 1 is just saying we want to read data from sheet 1, but since there's only one sheet, that's not necessary. But if you had an Excel sheet with a lot more, sheets you could specify, or you can specify 1 or 1 through 3. You can specify a range there as well. So our x will be just from 0 to 29, since we have 30. Yep, make sure to join the Slack channel. We'll have the recording there and on YouTube. And since we named our data A, we can just plot that as our Y data. And if we just plot that, so I just want to show you what MATLAB kind of defaults to if you just want to plot something just straight up, don't make any changes. Oh, don't want to do that. So make sure you save every time you make changes, otherwise it'll tell you to make a new file. I've only really run into that with the compiler. So if we just plot this, we just get a very plain, and you see it's called figure 1 because that's what MATLAB defaults to. Is figure 1, and if you plot something else after that, that'll be figure 2, and so on and so forth. And so it defaults to a line in this light blue color, and it doesn't really show us a whole lot. So we can actually make some changes. So we talked about line width, color. We can talk about line style, and also like marker edge, marker face. So if we plotted this, if we said, okay, line style, and so that's the line property. This is called a line property. We call it by its name, and the capitalization does matter usually. So you see here, it gives us some examples. So that's a solid line, that's dashed, that's dot dashed. So we'll make a dashed line, and color. So MATLAB, and you can look this up if you go to doc line style. So Smith plot. No clue what Smith plot is, but if we look up line properties on the MATLAB wiki, looking for, okay, so in color, so there are default letters, like R is equal to red, G is green, blue is blue. We can also actually put in an RGB value with a matrix like this, where first one is R, this is G, this is B. And that'll actually give us some really cool control over color, which if you're plotting, a lot of plots on the same, a lot of function in the same graph, like you can really like differentiate that. And that's stuff that you can all look up. Yeah, thank you, Bernard. You can all look up on the wiki. Sorry, my bar for Zoom is just covering all my stuff up here. Okay, so I hope everyone gets that. And I spent a lot of time on that, but I personally think it's really useful to know that you can like individually kind of control that. You can do it in the plot command, or we can call it like graph equals, just copy this. And then we can actually call this variable that now we're calling this plot function graph. You can graph.color equals, let's say we want it to be red. And then if we run that, invalid expression. Oh, let me just double check here. That should be fine. Graph.color. Actually have to call the graph.
You have an extra comma and line 4.
Oh, okay, cool. Thank you, Ray. Recognize property. Okay, now I'm just yelling out line 4 again. Oh, okay. Just gonna get rid of that. Okay, now it's red. Okay, took a little longer than I anticipated. I apologize. And so this will be useful then when we start actually getting into the little project we're going to do, which is figures can have GUI. So we can actually add toggle buttons to basically to turn the code on and off. Because what we're going to be doing is we're going to be using some matrix multiplication and a while loop to create a picture using a plot. And the picture we're going to be using is called a Barnsley Fern. And what's really cool about that is it basically just plots an iteration of points. And it can go on infinitely. And it's just based on some simple matrix transformations. So I'll just clear this. There's a function called image read. Here I will see. Here's the chat. Does that mean we just need to save the file with .m at the end? Yes, that'll save it as a MATLAB script. So I'm going to share. Oh, not sure if it's letting me share it. Hold on. Bernard, do you have the here? I'll send it to Bernard and he can share it. But there is a picture for matrix transformations.
Send it.
You sent it? Okay. So everyone can download that and drag and drop into the compiler, and we'll open that up together. It's called matrix transformations.png. And imread is just a function to open an image that you have in your file path. Oh, that's okay. We're going to stop that. I'm not sure why that's happening. I apologize, everyone. All right, anyway, you can, if you look at the matrix transformations, you'll see that when we multiply a 1 column 2 row vector by these 2 by 2 matrices, it'll basically move our points. So if we think of a 2 by 1 vector as being like our x and y points, it'll actually move it. What's the specified IM read line? I I was trying to get that to work. I might have mistyped it. Oh, it's image. Okay. I am read. Should have just been the file name. So I think I am read. So it gave us a bunch of numbers. Okay. I believe it reads the image, converts it to some other format, and then we can just type image. Okay, so here I'm saying f is equal to this IamRead function, and then we'll say image f. There we go. So you're able to open images in MATLAB is what I was trying to show, but we shared it in the chat so everyone can be able to look at it. Yeah, thank you, Bernard. Yeah, I completely fudged that up, but here. So I'll show the GUI once we actually get to the project. But anyway, so we're going to be making what's called a Barnsley Fern fractal. And it looks like this. And all it really is we're just going to be continuously multiplying a plotted point. So we'll say like x is equal to 1, y is equal to 1. And just transforming or moving its location using these transformations here. So, you know, if you look at the chart, you can kind of get an understanding of what multiplying by this 0.16, where it would move it. And similar to here. And so these are the matrices we'll be using in the fractal Fern. Yes, good question, Ray. And the GUI will get explained when we actually go through the fractal code. Bernard, you added the slide here. Did you want to explain this?
I think I went over that earlier. Like it's basically just saying the like multiplying elements versus just.
Oh, right, with the dot operator.
Yeah.
Okay, all right. So we're gonna get into the project, and I don't have to share this anymore. So this Barnsley Fern, it's basically just transforming. Gosh, I have this little tab with Zoom that just keeps coming down in front of my tabs up here. So we're gonna have a matrix x and y, and what we can just call like x, and we're just gonna be iterating. We're gonna be making a function that's gonna continuously just transform it, either by, you know, one of these 4 matrices. And so to start doing that, we're gonna make a function, or let's start by defining our x. So we'll pick 0.5, 0.5. Let's call this MATLAB Fern. So that's our x. And we want to define the transform matrices, which we'll just be using the same ones or similar ones that are here. So Thank you, Ray. So we'll just start with F1 here, which we can call it, because we'll call it like, yeah, let's call it F1. 0, 0, 0, 6, 2, actually have it saved here, so I'll be able to copy these. Yeah, the linear algebra isn't super important. What we want to show is a graph and showing that we can continuously add to a figure. So I'm taking I'm taking a lot of time typing these in. So I just realized I should probably be calling these A, just because the equation we're using is essentially this, which is that x is equal to A times x plus B. Because we also have these here. Okay, I'm going to copy these. Since I already have these saved here, there's no reason for me to type these all out and bore everyone. So these are our transformation matrices. A1. Yeah, got it. Put that in the chat.
Thank you.
Yeah. Save everyone some time. Okay. So we've defined our matrix transformations and our X. And so now we're going to have some fun actually making the function. So this is really all we need in this section of code. Let's also, yeah. So we're going to make a new, see, where's new? New function. And so when you make a new function, it actually gives you kind of a nice little, like Bernard talked about, the function setup. It actually kind of gives you the blank slate that you need to make your function. So we don't need an output argument because we're just going to be plotting. So let's call our function, let's call it call it Fern. And we're going to want to put in, we're going to call x1 and x2, which are just our first and our second part of our x vector or x matrix. And so let's see, let's get rid of our summaries. First thing we're going to do, this function is going to create a figure. Going to create a figure, and we're going to make a while loop that's going to continuously plot these transformations. And over time, if we had like an infinite number of transformations, it would create this Fern fractal that we see here. Okay. So we're gonna kind of redefine our x using x1, x2 to use in this function. And if we look at the Barnsley Fern, it says that each transformation has a certain probability of happening. So the stem has a very low probability of affecting the x vector, which makes sense because the stem is really thin and represents a much smaller area in the actual plot. So it makes sense that a lot of the smaller leaves and left and right side of the leaf are going to represent, there's a more probable chance that they're going to happen. So we'll make a matrix P, and that is going to be equal to our probabilities. And copy that. Oops. Send that in the chat as well. Oop. Okay. So that's the probability that any of these transformation matrices that we described earlier are going to take effect. So the next thing we need to do is we need to make a while loop that will iterate for as many counts as we want. So we see here that we make our initial plot. We'll set the size. There's a command called axes that'll actually set the x-min and max, y-min and max. And then so in our while loop, we're going to randomly generate a value between 0 and 1. And then we'll use if statements. So if our value is less than 0.85, we're going to plot this transformation. If it's less than this probability, plant the next one, and then anything else, we'll plot our last one, which is our stem. So really, this third probability value doesn't really matter because that'd be like a 100% probability. So the rest of these are always going to be, less than 1 except for 1. So that's kind of unnecessary, but we'll keep it in anyway. So does that make sense for everyone that we're going to be plotting our x, multiplying it by the transformation matrices that we defined here, and we're going to just be over. So in this example, I said like for 5,000 plotting points, we're going to plot these transformations. Okay, I'll take the silence as we're kind of getting it. So first thing we'll do is we'll actually start plotting before we start the while statement. I'll copy this as well. I'll share it. Oh, and so hold. I should explain that this hold function allows us to continue adding plots to the same figure. Because in effect, if we were to not have this on, when we finish, I'll show what happens if you don't have hold on. if hold was off, which it is by default, the figure would just constantly replace itself, and we would just see a single dot just adding every time, but there wouldn't be a finished picture. Then one other thing we're going to add before we start the while loop is something I briefly kind of brought up, and I didn't have a good way to kind of show an example before we got into the actual project, but in figures, you can actually add like GUI. You can add toggle buttons, and you can assign them different functions. So there's this, and again, this is something you can look up on documentation for like more specifics. But or basically, we're going to make a stop button, because if we're iterating this like transformation, like 10,000 times, in this case, we're going to do like 5,000 times. That could go on for a while. In this case, it'll only go on for like maybe 20 seconds. But if you had like 50,000, you would have plotted 50,000 points because you wanted the most perfect Fern. You wanted a solid Fern pretty much, with tons of points on the plotted figure. But you needed to stop it, or something interesting happens in a graph that you're doing for a class, and you need to stop at a certain point to show. We want to be able to interrupt this while loop. And so that's why the first if statement we're going to add in the while loop is get stop value, because the toggle button that we're going to make has a value of 1 if it's pressed down, and it'll increase the count to whatever we set our max to be, and it'll end the while loop, skip past all this, and plot one final plot. So I'm going to go ahead and okay. Thank you, Bernard. Thank you. That's a lot quicker than me adding bits and pieces to it. So if you download and then open that function, that createFern.m, and then go back to your, so we'll close out of that. We'll use createFern.m as our function. So what we can do now that we have all of this, which will create a figure, it'll create a toggle button, and then it'll, over a count of 5,000, it'll plot 5,000 points. It'll plot, we set color, let's see, color. Right, so the function x1, x2, which creates the x vector again for us to use, and then our transformation vectors, and then color. We can set color, we'll make it like a dark green. And this is something that we talked about before. We can make the colors, pretty much anything we want that exists within RGB values from 0 to 1. So we can actually now call create Fern, put in x1, x2. So putting in row 1, row 2, A1, A2, A3, A4, and then B1, B2, B3, and color. Now, if you run this, and here, actually at the top of here, it's always a good idea at the top of your scripts to add a clear and a clear command window. Just a helpful tip, especially if you have a really long code and you want to declutter your workspace. Closest match is okay, these up. Case sensitivity matters. So now you should be able to see in the compiler, or if you're using MATLAB in the actual application, it starts plotting all these points, and we can move this. We can move this around. When I wrote this code on the application for MATLAB, it wasn't quite covering the Fern. You see, it becomes denser up here. The stem goes all the way through here in the middle, and slowly but surely, you have a Fern. But let's say, oh, this is something cool. I want to stop it. We click the GUI. We stop it. It stops plotting. It ends the code because this while loop. We press stop. It sees that we press stop, and it ends the count. So that's the Barnsley Fern, and you can have fun with this. You can change the matrices and do different transformations, and there's probably a whole list out there of similar fractals, just with different transformations that create different shapes. Different probabilities, different shapes. Because I'm sure if we were to change the probability of like the stem and make it so that the stem, populates more quickly, or, it doesn't just have a probability of 0.01, it would have a much different shape. But yeah, so, this is an example of, creating a function, creating a figure, and then plotting all those points to a figure. And then again, the ability to actually change the line type, shape, color, everything that we're plotting, which actually, let's do something fun, just super quick. I don't want to see what it looks like. Let's change the shape. Let's make it a star, because why not? I'm just curious to see what it looks like. Yep, and we'll go through some signal processing, because that's the stuff that will really, beyond like data and analysis, like this kind of stuff, it'll really make a difference when you have things in class. So I'm just going to save that. Ooh, looks kind of cool. All right, so I hope you guys had fun with that. And if there's any more questions, feel free to add them in the chat, and I'll be able to answer them. And I will stop sharing, and I'll hand it over to Ray.
Okay, everyone. So we know that MATLAB is so powerful to do all these matrices and plotting maybe, but we as engineers don't use these things just for plotting. There's so much usefulness into MATLAB. It's used for probability, it's used for data acquisition, it's used for dealing with signals. It also has Simulink. You can use it in control systems. You can use it for machine learning. But as ECE people, we use it a lot for signal processing. How many ECEs do we have in the moment right now? Like, raise your hands, like with the emote. Okay. Mechanical engineering, yes. Nice. Okay, so we have a good variety. So I'm gonna go on and share my screen, and then I'm going to show you this thingy. So there is something, if you're not a pre-junior, you probably haven't learned this stuff yet. So if some stuff goes over your head, just don't worry about it. The idea is how to use MATLAB, and what I want from all of you is that if you ever get to study this at like a future class, you're like, oh yeah, I remember I did this. Like, this is doable with MATLAB, and it is very easy. So a system has a response. So let's say a very simple way for me to put it is, if I kick myself, I'm gonna shout because it hurts. So this shouting is my impulse response, let's say, my way of responding to the thing that happened. But in signals, we have this more formal way of dealing with them, and they're usually called transfer functions. So, for example, in this circuit up here, this is an op-amp, these are op-amps, and this is called a low-pass filter, and this is called a high-pass filter. So the idea is that when we have an RC circuit, if you remember from physics, or an RL circuit, we deal with frequencies, with alternative currents. So when we pass low frequencies in this one, these allows them to pass. But when we pass high frequencies in here of AC current, this does not allow them. So here at R4, we only have low frequencies. And then at R4, we have a high pass frequency. So this is also not going to allow the high pass frequencies. So this is going to give us what is called a band pass filter, that is going to allow only a band of frequencies. And it is very useful. And the way to study these things is transfer functions and body plots. So we will explain with MATLAB how to get these body plots. And I will jump straight across to getting these plots over here. So I'm going to close this down, and I'm going to start a new share. I'm going to create a whiteboard. So the transfer functions that we're going to use, for now, don't worry at all how we got this. Just take a piece of paper and put them in there. So the frequency response of a low pass filter, the transfer function is going to be negative R1, R2, and I'm going to send the values of R1, R2, R3, and R4 that you need. And actually, let me do something. This is J omega, and the high pass is going to be negative R2 J omega L, and it's going to be divided by R4 J omega L plus R2 R4. Now, if you notice, what is this J omega? J is imaginary number, but we as electrical engineer do not use I because we use it for current. So J is going to be the square root of -1. And L is an inductor and C is a capacitor, right? This is high pass here. And this, we get these transfer functions by a mathematical method called Fourier Transform. And the Fourier Transform is in the J omega axis, where J is the imaginary number, as we said, omega is the frequency in radians. But in MATLAB, we use Laplace transform. And to make it very, very simple, don't worry about this. Fourier transform is just Laplace transform evaluated at this. So when we plug this thing in MATLAB, we're going to substitute all J omegas with S. Remember this. Now let's go back to MATLAB and start doing some coding. Now, where's my MATLAB? Okay, I found it. plot. Where's the chat? Chat. I lost it. Okay, I found it. I'm having some trouble popping up the chat. Okay. Okay. So these are the values of R1, R2, R3, and 4, and the capacitor values, and they are respectively, the units are ohms, farads, and henries. So now, if you remember, I'm going to go here, open a new file, and then create all of this thing with you guys, and we can also show some plotting here and everything. Now, this is the long way to do it, and the long way to do it is what we use. Wait. Why can't I open the chat?
If you go to your bar at wherever you have share screen, you have to click more options or view options, and then chat will show up. That's what I had difficulty with earlier. It doesn't, when you actually share your screen, it is harder to see the chat. So if you guys have professors who say that, like, if they're sharing a screen, they're not gonna be able to see the chat, it is actually more difficult to see the chat. There's no notifications.
Okay, so I'm gonna do this and reshare my screen. Okay, let's see if this works better. Okay, so this is the long way. So the long way is we write the impulse responses, right? The transfer functions of each, right? As I said, this is the low pass and this is the high pass. So we manually plug it in there. After plugging it there, we need to find the total impulse response. And we know that by Fourier transform, when we have two cascaded systems, the overall transfer function is the multiplication of each individual system. So here, if you notice, this is the first system, and we do dot product, dot multiplication of each. Don't worry about this now. This is probably very complicated and it's not the best way to do it. But I just want to show you this. When I did this for the first time, this is how I did it, and it is a bit painful. We get the total impulse response. Now we need to find the magnitude and phase of this transfer function. So in MATLAB, we have a function called absolute, abs, that is going to give us the absolute value of a function at any point, basically. And for when we deal with imaginary numbers, we know that an imaginary number has a magnitude and has an angle, which is called phase in engineering differently. So we find the magnitude by using the abs ht, and we find the angle, or rather the phase, by using the angle function. So we say angle ht, and this is going to give us the answer in radians. So I want to change it in degrees, so I multiply by 100 and divide it by pi, just so I get it in degrees, because only this part is going to give you in radians. Now we know that body plots is a sort of logarithmic scale plot that we use because we deal with frequencies from 1 to 10 to the power of 6, which is around 100,000 probably, 100,000 or a million, something like that. I think it's a million. So the magnitude of that, we change it in a logarithmic scale, right? So whatever we had here, we multiplied by 20 times log base 10. And now we're going to do plotting. So as we said earlier, we declare figure, because we want to keep all of it. And I want a subplot of 2, 1, so 2 rows, 1 column, 2 rows, 1 column. And for the first plot, you can, instead of the common plot that we do, right, we can say something called semilog x. And what semilog x does is that it only plots x as logarithmic scale. If we did semilog y, it would only plot y as logarithmic scale. But we only want x, so we're going to use semilog x, and everything else is the same, because plot and semilog x is just a modification of plot. So you guys can still declare colors, you can still change the line style, you can add dash dash there, you can add you can change the width. Now here I've also created 2 vertical lines. I personally love these lines because they help me a lot where the function gets cut at certain values. So I use it. So x line is going to give you a vertical line at that point, so at 1000, so 10 to the power of 3, and 10,000, 10 to the power of 4. If you do y line, it's going to give you a horizontal line, right? And then we do x label, which is going to name the x of the subplot, the x-axis, and the y-axis. Now, this is something cool that I found out. So if you guys ever want to seem a bit fancy to your professor and want to make Greek letters cool in graphs, you can simply write at, for example, here at the x label, you can write frequency here, and you need to do what is this called, Chris? Backslash. So we do backslash, and this is an escape sequence in MATLAB. That's what it is called, backslash omega. And this is gonna output the omega Greek letters. So we have it here. So that's cool. You can do it with pi, with anything, right? Just, I don't know. I love it how it looks, so I just make it. So this is the super title as explained by Bernard before. So this gives a very big title. I didn't add titles each, but I can add, for example, so I can run it again. So I can say title. This one is going to be magnitude. And phase. And the second one is exactly the same, but it's just the second graph. And we plot now the angle that we found up here. With respect to the x. So if I run this, I should just get the same thing, but I should just have the titles on now, probably. Yep. So now this is a very long way how to do it. Now we're going to show the short way. This is called a body plot. So basically, as I explained before, these are the low frequencies here from 1 to 100, and these are the high frequencies here. And as I said, what we created in the circuit, it does not allow low frequencies to pass, and it does not allow high frequencies to pass. So this is a band pass filter. Don't worry too much what it means. It's just something cool. But how can you do this very shortly with MATLAB? With MATLAB, we're just going, so this I want you guys to actually do because I think it is interesting. So here we have the values as we said, and now I'm going to go share my screen again. So if you remember, now here, imagine the transfer functions as the division of 2 polynomials. The polynomials, let's say AS and BS. I chose the wrong letters, but it's fine. Okay, so in here, this is a polynomial of degree 1, right? It's just, for this one, we just have negative R1. But this one is a polynomial of degree 2, the denominator, because we have, this is of the form ax plus t0, right? So x in this case is j omega, a is r1, r2, c, and t0 is just r2 here. So now we can do something in MATLAB that can just input this function itself. So let's go back to MATLAB. If everybody has the functions in their what is called, written down in a piece of paper, now we say h1 is tf, which means transfer function. We open parentheses, and now I'm going to rewrite it again here, so I explain it while I see. So transfer function, and then we open parentheses, and the first brackets, the set of brackets, is going to be the numerator, and the second set of brackets is going to be the denominator. So the first set, as we said, the numerator had just one, so negative r1, because that is what it is. And the denominator, it was the coefficient. We need to put them from the highest degree to the lowest degree. So let's say that I had s squared plus s minus 1 plus 3s. And this was the denominator here. I would say that this one here would be 1, 3, negative 1, which means 1s squared plus 3s minus 1. And this is very common in MATLAB. You can use this to find roots, for example. So just so you know. So I'm just going to input the thing that we have. So the first one, as we said, was R1 times R2 times C. This was AX here. And R2 was the T0. So if we do that, and now we can just say body H1. It is that simple. And I can turn grid on here. And now I do this also for the second H2, for the high pass filter. And here, if you notice, at H2 in the numerator, we had negative R2 times L times J omega. So I put negative R2 times L, and this represents J omega. And if this is very important, you need to put 0 here, so you show that this is a polynomial of the form ax plus t. Because if you don't put this, this will just use this as a constant, just as a t, right? And in the numerator, we have, again, two numbers. So this is a is r4 times l times s, and this is just the coefficient afterwards. And we plot here body H2. And then if we want to get the total transfer function, we just multiply them exactly like we did before. And we just press body of the transfer function like that. And if we run this, this is a low pass filter. It's going to allow the low frequencies. This is a high pass filter. And this is a combination of them. And if you notice here, it is the same exact graph that we had here. And this one took us 57 lines. This one took us not even 18 lines. You could probably do it like this. So I just wanted to showcase this, that this is the power of MATLAB for electrical engineering. This is a way to use it. And if you want to do something with MATLAB, there's a very high chance somebody has done it before you. So I just suggest how to, and it is the most documented language because the license of MATLAB costs millions of dollars. So there's actually people getting paid to put documentation every day. And you can just search, for example, how to plot a 3D plot, how to make an animation, how to make a body diagram, right? And I think that MATLAB is a very useful tool as an engineer. I think it gets a lot of hate. I know that the index starts at 1 instead of 0 like every other language, but I hope that this workshop showed how useful it is and important to us as engineers, and hope you use it more. Actually, I wanted to thank Chris and Bernard a lot for this workshop, and if you have any questions, let me know, let Chris know. I'll putting the code here in the chat, and feel free to discuss, to ask anything else you want. If not, I guess that's the end of it.
Thank you very much. I learned a lot.
Before you guys leave, I would really appreciate it if you could fill in the feedback form. I'm asking Bernard currently to put it there. Also, we are looking for people to join the workshop committee. So if you have new ideas and want to organize your own workshops, feel free to contact me. My email is this one. I'm putting it in the chat. Feel free to shoot me an email anytime and we can discuss, and you can become part of the workshop committee, discuss what you want to do, and let's just try and have a good time. Intersection of two data sets. Okay, so I'm going to do something that I always do when I don't know. Data sets, MATLAB. And this is the code about it. They just give you everything, right? As I told you, like, this language is incredibly well documented, and you input the data here, and I'm reading the code. There's like the subset A. That's a lot of data. I don't know, this guy needs it for. This is subset data 2. Okay, so this is the answer, I guess. I have not used it myself. Here, this is for 2 columns. So because if you notice, the data here has 2 columns, 2 numbers. So the int x, int y, this is going to give you all the intersection points. So here you say intersections, data 1 column 1, data 1 column 2, and match this with data 2 column 1, data 2 column 2. And this is the output. And he goes on and on, like, explains. He also does it this way. So if you ever feel like you don't know something in MATLAB, just Google it like I did, and you're gonna find a very detailed answer like this. I don't know if that helps. Awesome. Okay, Bernard put the feedback form. So please fill in that. If you want to join the workshop committee, please do send me an email. And if you have any questions, we're going to stick for another 5 minutes. And after that, I guess we were going to call it a day.